An eigenvalue is the characteristic value of a matrix equation, or the characteristic value of a matrix. In today's lesson, I will show you how to calculate the eigenvalues, and I will show you what they are. Now, with each eigenvalue, you have an eigenvector. I'll also show you how to get the eigenvectors. Later on in the course, we'll revisit eigenvalues and eigenvectors with more applications. Let A be an n by n matrix. In other words, A is a square matrix of dimension n. And let X be a non-zero n by 1 column matrix. So A is an n by n square matrix. X is an n by 1 column matrix. And X is not the zero matrix. If there exists a scalar, we'll call the scalar lambda, such that AX is equal to lambda X, then lambda is called an eigenvalue of A. So either eigenvalue or characteristic value of A. And X is the eigenvector. So in one way of looking at it, I'm trying to find a scalar lambda that would take the place of the matrix A. And if I can find the scalar lambda that takes the place of the matrix A, then lambda is the characteristic value of A, or the eigenvalue of A. Then X will be the eigenvector corresponding to lambda. So every eigenvalue has a corresponding eigenvector. Well, we can use determinants to find out the values of lambda. Let's start with just some properties of matrices. If AX is equal to lambda X, then lambda X minus AX is equal to 0. So what I do is I simply subtract AX from both sides. So subtract AX, AX minus AX is 0, lambda X minus AX, of course, is lambda X minus AX. Now if lambda X minus AX is equal to 0, then I would have lambda IX minus AX is equal to 0, because I can multiply X by the identity matrix without changing the value. So lambda IX minus AX is equal to 0. Now we have a common factor here of X, so using the distributive property of matrix multiplication over addition, see this is the same as plus to negative, so I can do that. I can factor out the X. So I have lambda I minus A times X is equal to 0. Now, we have a homogeneous system of equations. The homogeneous system of equations has non-zero solutions if and only if lambda I minus A is singular. So if lambda I minus A is not singular, then this system of equations will have a unique solution set. If it has a unique solution set, then that solution set has to be the set of zeros. In other words, all the values of all the components of X would have to equal to 0, because we know that the trivial solution with X equals 0 would make it true. So if this has only one solution, it's the trivial. So if it's going to have non-zero solutions, then it must be singular. Well, if lambda I minus a is singular, then the determinant of lambda I minus a is equal to 0. I proved that for you on the last tape. So the n by n matrix A will have a maximum of n eigenvalues if we can find a value lambda such that the determinant of lambda I minus a is equal to 0. Find the eigenvalues and eigenvectors of the matrix A is equal to 2, 0, 1, 0, 3, 4, 0, 0, 1. Well, we want to find lambda such that the determinant of lambda I minus A is equal to 0. So that's what we proved on the last sheet. We want the determinant of lambda I minus A to equal to 0. So this would be lambda times I, which is 1, 0, 0, 0, 1, 0, 0, 0, 1, minus A, 2, 0, 1, 0, 3, 4, 0, 0, 1. So we want this determinant to be 0. So this is lambda I minus A. Well, this is going to be lambda, because I multiply the scalar by each of the entries in the matrix. Lambda, 0, 0, 0, lambda, 0, 0, 0, lambda, minus the A, 2, 0, 1, 0, 3, 4, 0, 0, 1. It's still equal to 0. Lambda minus 2, well, I can do the subtraction here. 0 minus 0, 0 minus 1. 0 minus 0, lambda minus 3, 0 minus 4. 0 minus 0, 0 minus 0, lambda minus 1 is equal to 0. Okay, so note that we have the determinant of AI minus lambda. So what we have here would be the AI minus lambda matrix, and we're taking the determinant of the the lambda I minus A matrix. Now notice that this matrix is upper triangular, so that I can get the determinant by simply multiplying along the diagonal. So I would have lambda minus 2, lambda minus 3, lambda minus 1 is equal to 0. Or I have lambda is equal to 2, lambda is equal to 3, lambda is equal to 1. So I get the 3 eigenvalues. In a 3 by 3 system, we have a maximum of 3 eigenvalues, so this is all we could possibly have. So the first part was to find the eigenvalues. Now we need to find the eigenvector associated with each eigenvalue. So first, we'll consider that for lambda is equal to 2. Well, we know that lambda I minus A times x is equal to 0. Going back to this, lambda I minus A times x is equal to 0, and x will be the eigenvector that I'm looking for. Lambda I minus A is simply the matrix that we're taking the determinant of here. So I've already calculated that once, so I'll just rewrite it. We have lambda minus 2, 0, negative 1, 0, lambda minus 3, negative 4, 0, 0, lambda minus 1, times the X matrix, and we'll call the X matrix X, Y, and Z, is equal to the 0 matrix, 0, 0, 0. Now for lambda equal to 2, 2 minus 2 is 0. That would be 0, negative 1, 0. 2 minus 3 is negative 1, and negative 4, 0, 0. 2 minus 1 is 1. I'm just, lambda b 2 minus 2 is 0, 2 minus 3 is negative 1, 2 minus 1 is 1, times x, y, z is equal to the 0 column matrix. Okay, doing the multiplying and then equating elements, this be 0x plus 0y minus z is equal to 0. 0x minus y minus 4z is equal to 0. 0x plus 0y plus z is equal to 0. Now we can see from these two that z must be 0. From this one, I can see that y is equal to negative 4z, which is negative 4 times 0, which must be 0. So z must be 0, y must be 0, but x can be anything because there's no x's involved. So I'll just let x be 1. So the eigenvector corresponding to the eigenvalue 2 can be the column matrix 1, 0, 0. Now I just let x be 1. This could be any number really. Now, let's let lambda be 3. And we want to get the vector associated with lambda being 3. Again, we're going to have all lambda I minus a times x is equal to 0. Well, if lambda is 3, here's my lambda I minus a matrix, so I'm just going to substitute in now. If lambda is 3, 3 minus 2 is negative 1. That would be 0, negative 1, 0. Lambda minus 3 is 0, negative 4, 0, 0, 2. Lambda is 3, 3 minus 1 is 2, times x, y, z is equal to the 0 matrix. Doing the same thing, this would be the opposite of x plus 0y minus z is equal to 0. 0x, 0y minus 4z is equal to 0. 0x plus 0y plus 2z is equal to 0. Well, if 2z is equal to 0, so we see obviously that z is 0. We see that x is the opposite of z, which implies that x is 0. It doesn't mention y. So I can let y be anything I want to, and I'll pick 1. Now I can't let y be 0 because the eigenvector x has to be non-zero. So I can't have all zeros. So then x, the eigenvector, associated with the eigenvalue 3 is going to be the vector 0, 1, 0. Now, let's look for lambda equal to 1. In other words, ai minus lambda times x equals 0 for lambda is equal to 1. 1 minus 2 is negative 1. One minus 3 is, well, that'll be 0, then negative 1. And then 0, 1 minus 3 is negative 2. 1 minus 1 is, well, that would be a negative 4. Jumping ahead of myself, then it would be 0, 0. And now, 1 minus 1 is 0. And I just see where I made a mistake in the other problem. It doesn't affect the answer. Look back when I was doing, I let lambda be 3, and I did 3 minus 2 and got negative 1. That should have been plus 1. This is going to come down and be plus x, which means that x is equal to positive z, which is still 0, but do make that correction. Now let's check this one before we continue. We're doing lambda is 1. So 1 minus 2 is negative 1. Be 0, negative 1. 0. 1 minus 3 is negative 2. Then that'd be negative 4. 0, 0. 1 minus 1 is 0. Times the x is equal to 0. Now that means the opposite of x plus 0y minus z is equal to 0. 0x minus 2y minus 4z is equal to 0. 0x, 0y, 0z is equal to 0. So I just get 0 equals 0 for the one on the bottom. So we can see here that x is going to be the opposite of z. I get that 2y is equal to the opposite of 4z, or that y is equal to a negative 2z. Well, we'll let z equal to 1, and we can get x associated with 1 is going to be, z is 1, x is opposite of z, that would be a negative 1, and y would be then a negative 2. So there's my third eigenvector, the eigenvector associated with the eigenvalue of 1.